day 5 of the meeting. And the first talk is by Henning towards molecular complexity.
Yeah, first of all, I wanted to thank the organizers for inviting me. I had a 30-year break before I could come back to Bulgaria. It's a great pleasure to be here and to attend another Origins of Life meeting. One of our most fundamental questions is actually how the magma-covered early Earth or other terrestrial planets transited to systems like we have today, which are biogeochemical systems. Now, I'll show you this image you have seen many, many times, because in a couple of weeks from now, we will celebrate the 50th anniversary of this wonderful image from Apollo 17. And a lot of 17s in the numbers, so you can certainly remember now the date of the birth of this image. The important information we actually have, and I find it always amazing, that shortly after the moon forming event, life occurred. So it didn't wait for another 4 billion years, it was shortly after, and that means that we have to characterize and understand the conditions of early Earth or early terrestrial planets, and we also have to find out what the impact of material is. So you certainly realize that I'm an astronomer, so I will go back to prebiotic chemistry and I will not talk about cells. We have seen a lot of definitions, and I show another one, which is sometimes called the NASA definition, which is not completely correct because it goes back to Gerald Joyce and a working group. And I really like this definition, but I should point out that so far we couldn't find an artificial chemical system undergoing Darwinian evolution, and we have seen in the previous talk that we not only need this definition, but we certainly also need some containers, some cooperative effects, and I think that we can learn from synthetic chemistry. We had actually interesting discussion about neutral evolution, I think 2 days ago, and I will not dive into that, but I will just mention that neutral evolution refers to the molecular level and not to the biological level. So we have two possibilities to bring material to the early Earth. I mean, one is, of course, to produce material under the conditions of early Earth. The other possibility is that we bring material from meteorites or asteroids to early Earth, and from geochemistry, we have actually the hypothesis that we have a late veneer where we bring in chondritic material, iron-rich material, which is then able to reduce the components we have in our slightly reducing atmosphere. However, I would like to point out that we don't know exactly when that was and how it was. So the size of the bodies entering the atmosphere are not very well constrained, although we have some constraints. And we also don't know how much volatile-rich material entered the atmosphere. So I just wanted to show one cell image because I'm in the cell session. I just wanted to point out that cells are really very packed systems, very complicated systems, and therefore I very much like the previous talk where we're trying to simplify the systems and see what kind of effects we can then actually study. So here I have my prebiotic molecules. In another talk yesterday, we already heard that water is a good solvent, but I would like to make another point. Water is also abundant in the universe. That is important because water consists, of course, of hydrogen and oxygen, but we see water all over the place. We see water in storming regions and planet-forming disks. The water is abundant. If you would like to go to the next solvent, to hydrocarbons, they are much less abundant than water. So it's not only that water is abundant, it's good for chemistry, it's also that it is actually available. And then we have discussed hydrogen cyanide. Just to remind you why HCN is important, you can remove one hydrogen atom, then you have a nucleophile molecule, and that can actually establish carbon bonds. It is actually important to note that it may not only be hydrogen cyanide which can take this action. So I contradict a little bit John Sutherland's statement that you absolutely need HCN. There are also other molecules which will be shown very soon in a paper by Sidney Becker. Then formamide is another important molecule, and then you would like to go to the next dimension we have here in this slide as well. I always show this slide because this is a heterogeneous community, and if you go to the astronomers in the room, you will actually not know how RNA and DNA is composed of, and you see it here. You practically have our nucleobases, we have ribose, and we have phosphate. And I just wanted to point out that we should not have this naive picture that we mix everything together and then we have RNA. Of course, that will not work, and it has demonstrated that it will not work. So you need a more complex cooperative chemistry to write your RNA. So if we talk about information, I just pointed out that we have two possibilities: supply of material or formation under early Earth conditions. We have our atmosphere, CO2 atmosphere, water, and nitrogen, and we want to form all these molecules. There are quite a number of studies now for HCN and formaldehyde, for instance, but very little for the sulfur-containing components. And I also wanted to add that it is always important that your chemistry is actually occurring under geochemical conditions, and I very much like the paper by David Kettling and Toner, where they actually show that high carbonate lakes can solve the phosphate problem, which is normally then an appetite, but in this case it's not. So there are now two models which are relatively comprehensive for the HCN formation. One is a late veneer-based impact model, but it doesn't calculate the atmosphere conditions. It's only treating the chemistry, and the problem with the model could well be that if you form a lot of molecular hydrogen and methane, which is a greenhouse gas, your atmosphere starts to boil, and you will not have lakes at the surface because you produce very high temperatures. So in the model we developed, we actually coupled the atmosphere, we used photochemistry, and then the result is yes, you can form HCN, but not a high amount. And the question to the chemist would be, is a small amount sufficient to trigger chemistry in a fluid system? Just to show you that there is indeed HCN in other environments. That's actually an image of Titan, and this little blue dot you see is emission from HCN. So the next steps would be that you go from HCN then to other materials like ribose, and I've just mentioned a few. I really wanted to highlight the paper by Beckedel again, who could produce pyrimidines and purine-based RNA nucleotides from HCCN. So now let me move to astronomy. This is actually an image of a star-forming region, very cold temperatures of about 10 K, densities of about a few hundred particles per cubic centimeter. And here you just see a collection of molecules we discovered. Just let me highlight formamide and formaldehyde, and other groups have done the same. So in these star-forming region, there is a soup of molecular molecules which are actually relatively complex. You could now ask the question, what has this to do with my planet-forming environment? But before I talk about that, I just wanted to show you what kind of chemistry we actually have. We have two types of chemistry. One operates in gas phase, and for the normal chemist, she or he would ask, why is there any chemistry at 10 K at these low densities? And the answer is because we have cosmic rays. Cosmic rays bring energy, ionize molecular hydrogen, and then you have proton transfer reactions and a whole bunch of ion chemistry. The other possibility is that your chemistry occurs on small dust particles, sizes of about 0.1 micron, and in these ice mantles you can then form a lot of complex molecules by radical chemistry, hydrogen addition, or other processes. Just to show you one example from the lab, that is actually coming from Cornelia Meinert's experiment a couple years back. So she did an experiment where she irradiated such an ice particle and then could demonstrate that you form ribose in such an environment, and indeed glycoaldehyde was actually also discovered by astronomical observations. So what has this to do with our environment where we think planets form? This is now a comparison of the abundances between star-forming regions and comets. So what you see is its normalized abundance, and what you see here that these abundances actually correlate quite well if you go here, and that is a very strong argument that the initial organic reservoir of the solar system and other planetary systems is actually produced in a previous step where you form the star. Of course, that's not the complete truth. You will also have chemistry in your planet-forming disk, but I think it's intriguing to think that your water molecule you drink at the moment was actually produced a billion years ago somewhere in a star-forming cloud where the solar system formed. So we have also discovered molecules in planet-forming disks. This is much more difficult. The reason is very simple. These disks are small compared to star-forming regions, so you need enormous sensitivity. And ALMA is the only machine which actually can provide this sensitivity. And you see that we have, for instance, discovered formic acid, but also other components like acetaldehyde and acetones in planet-forming disks. But there are even larger molecules available. For the smokers in the room, pHs. You can easily produce pHs when you smoke. They are very cancerogenic, so you should better not smoke. But these molecules have been discovered in planet-forming disks. And we have also analyzed different families. They are normally quite large and provide, in a way, the first surface for chemical reactions. But you can also go to the near-infrared, not to the radio, and these are actually the old spectra from Spitzer. And what we found, and I think that's very important to realize, that the molecular content of your planet-forming disk may depend on the spectral type or the mass of your central star. And that's nicely demonstrated here. We have actually acetylene and HCN. You see a lot of HCN in sunlight star, and here in the cool star you practically see nothing. And I can tell you, but I'm not allowed to show you a spectrum, that our first spectra of disks around brown dwarfs show enormous families of hydrocarbons. There is enormous hydrocarbon chemistry in these low mass disks, in contrast to disks around solar-type stars. So it's not only the star which has different radiations, but I think it's also chemistry in the disk which is different. So we have different initial conditions. Just to show you that in these disks where we could actually discover a lot of water, so all these lines here is not noise. Every line is actually a water line. And we see the same now with our JWST data. You can actually also get isotopic ratios on this JWST data. And for one of the disks, we already found that the isotopic ratio is actually not the same as in the interstellar medium, which points to changes during the planet formation process. So we also have molecular ices, so these are absorption spectra. So if you have a disk edge on, you can actually get absorption spectroscopy. And you see here carbon dioxide, methanol ice, NH3 ice is all present in these environments. And if you do the same exercise for the ices, you again find that comets and interstellar ices have very similar abundances, which is another argument for the fact that many of these molecules come from the star-forming region. So Rosetta was really a Rosetta Stone for organic chemistry of molecules. This was the first time that we did a very detailed mass spec of a comet. It was actually not the first time that we did mass spec of a comet. That has been done for Halley, actually with instruments which were developed in my neighboring institute in Antwerp. But here we see a lot of groups, and you see again amines or amines and we also have glycine in this environment. I just wanted to mention there's of course another external source of complex molecules, and these are the parent bodies of meteorites. And as I already alluded to, we actually don't know how much of this organic material entered early Earth. We think very little, but there are also counter-arguments, and that remains an open question. But what I found amazing is that in this environment, which is practically liquid chemistry, you have now all the amino acids, you have sugars, you have nucleobases, and there was even a recent paper which claimed that there are proteins in these environments. So what we actually did, and you had a talk about this, about the Foremost reaction. We actually used the Foremost reaction, which is now 80 years old, and we are still working on this to understand the reaction, because it has a lot of side reactions. So it's the self-condensation of formaldehyde as a catalyst, and there are also other ways to do that, like mechanochemical sugar synthesis. But we put that in a chemical network, mostly equilibrium chemistry, because the asteroids are at elevated temperatures. And then we had a detailed asteroid model, and we could actually reproduce the nucleobase and ribo abundances in these meteorites quite well. So we didn't have to tweak anything. It was just based on first principles and the initial abundances we could actually try to determine. So that's another environment. So now let's make a jump to the lab. Let's see what we can do in these molecular ice experiments, and I already showed you one result from Denise's group. So normally these experiments are based on UHV chambers. You have then a characterization stage up at infrared spectroscopy, mass spec, to characterize your products. So examples of this work are actually hydrogenation studies to form formaldehyde and methanol. We now also know that the result depends actually on the surfaces you have. But I feel that this is mostly done. We somehow understand how you can form these abundant molecules in molecular ices. The next step is, of course, to do reaction kinetics. So we actually proposed a completely new way to get reaction kinetics at very low temperatures. I don't have enough time to discuss this, but what we have seen is that many of these reactions with atomic carbon do not have any barrier at low temperatures. This was not really expected, but you can form many molecules under these conditions, and you can actually measure the reaction rates very precisely in these systems. So I talked about formamide, and this is another example. So what we did here is we actually studied CO, ammonia, water ice mixtures, and in contrast to the gas phase channel where the reaction rates are practically not known, we could then find very efficient production of formamide in these ices. We also see then byproducts like OCN-, which was hypothesized by infrared spectroscopy in the past, and a few other molecules, but the main product is formamide. And it's also interesting that it is very efficient if you have water ice. If you go to CO ice, then it is much less efficient, and we think that water ice is actually a dominating component. So now let's do one step further. Let's ask the question, can you actually form peptides under these conditions? If you would have asked me 2 years ago, I would have said no. I mean, you have to do that in a liquid system. You have somehow to remove water. So we had a wonderful talk by Matt Powner about that. But here we are. So we have actually designed an experiment where we found peptides. And it starts with the same setup I already mentioned. You have a substrate which is at low temperature, and we have a carbon source, and we have a source of ammonia and CO. So why did we select ammonia and CO? These are abundant molecules. They are in the ices, as we know, and atomic carbon is around as well. So this is not a very artificial system, and it's a very simple system as well. So then we did first infrared spectroscopy. This is just to see if we can actually produce new materials. And the red line is actually the line where we have seen new stuff in the spectrum compared to a situation where we only mix two of the components. And then, of course, what you normally do is you do TPD measurements, so you heat it up and you do mass spec, and then you find aminocation. And if you then go to the orbit trap, we actually find a mass number of 189, which is actually the first peptide of a system based in glycine. And then you also see that we had different lengths of the peptide system here. And there are different end groups, either NH2 or CH2, and that was clarified by higher energy C-trap dissociation, but that would need another talk. So I just wanted to end with a slide about an experiment which has been done in Oliver Trupp's group, who is an associated scientist to our institute, and he actually started with relatively simple material and could then build up DNA and RNA precursors. I really recommend to go to this paper. And then some shameless advertisement, because we heard a lot about the Harvard Initiative for the Origins of Life. We were also on the early birds. So we have the Heidelberg, not the Harvard Initiative for the Origins of Life, going back from planet formation, planetary atmospheres to RNA and DNA synthesis. And we even succeeded to get the Harvard addition to our institute, Laura Kreitberg, who is now doing the planetary atmospheres. So I leave you with a very important complex molecule for higher life, and thank you for your attention.
Okay. Yeah, this is Lauren. That was an incredible talk. Thank you very much. I would just like to point out this kind of weird thing I've been sensing at this meeting, and you demonstrated this too. It seems like there's many ways of synthesizing peptides. Basically peptides are easy. Matt Mallory's work, and you've done a bunch of dry down experiments, and you've done it here. And we've also just heard two talks that suggest that chemical evolution does not require nucleotides. And maybe it sounds harsh, but we've had 50 years of organic chemists going out of their minds, talented organic chemists trying to make RNA by non-evolutionary methods. And I'm just wondering if something is not adding up here. I'm just wondering if you have comments on that.
Yeah, I personally think that this dichotomy between the RNA world and the peptide protein world is not the right description for what we see, because it's certainly a co-evolution of both. But what we do at the moment, and I think we also have seen that in other talks, still to screen a bit the chemistry which is possible, because nobody did such an experiment at low temperatures, and that is mostly triggered by the observations of what we see in comets. When I saw the glycine, I thought, well, why not the next step, but there was no experiment, and at some point you have to do an experiment. The calculation could also be that there's a huge barrier that you couldn't form the polypeptide. So I just take this, just have to fill in the corners.
Okay. Antoinette and Don Institute of Astronomy and Academic Sciences. I'd like to go back a bit to the astronomical stuff. We were talking about the different chemical composition in this around different spectral types of stars. You base these results on studies of different spectral types in the same star formation, I presume?
Now, what we do, we have a big JWST program, but we also did a lot of Spitzer work. So you practically take stars of different masses, ranging actually from non-stars, brown dwarfs, to low-mass stars, to intermediate mass stars. And what we see, there are differences, big differences between the chemistry in these disks. And I would say these are early days. I mean, these are the first JWST spectra. So let's see. But if that turns out to be true, I think we have different reservoirs in which we form planets, you know, and that has to be taken into account.
Yeah, this is my follow-up question. So would that be due to the energy emitted by the star or the different energetics of the star?
So there are two possibilities. One possibility is the mass of these disks is correlated with the mass of the stars. That we know. So low mass objects have low mass disks, which means they have low optical depths. So radiation can penetrate into the disk much easier than in other systems. So that could be one explanation. But during the meeting, we also heard that M stars are very active, for instance. I mean, going to the TRAPPIST-centered star, this is a very active star. The sun is active, but it's much less active compared to this M star.
Yeah.
So I think it would be two reasons, either the disk properties or the stellar properties.
Yeah, well, I'd like to discuss this a little bit further after
Okay,
that.
okay.
Thank you.
Really, there are other questions?
Thomas, great talk. About these fascinating results on the disks again, you mentioned the isotopic differences issue. What is your opinion? Is it due to the different type of grains that you form in these disks, or is it thermal cycling that produces those isotopic differences?
I mean, isotopic differences are normally produced if you have low temperature reactions because of the shift of zero point energy. So we know that actually from molecular clouds, from radio spectroscopy. So it argues in a direction that this material really formed at low temperatures and not at high temperatures. And I think I have now a lot of sympathy for that, because what we recently showed is if you have pebbles, which are practical containers, transporting this material from the outer to the inner disk, nothing happens. There is no chemistry going on, and that is because of timescales. So the timescales of drift are much faster, the timescale of chemistry is much faster than the drift timescales, and nothing happens. So the containers practically bring the pristine material from the outer disk to the inner disk, and at some point it evaporates.
I want to say I couldn't agree with Lauren's comment more, and I'm so glad that you looked at the peptides. I've been asking for years about abiotic production of peptides. The response I kept getting was, oh, we didn't bother to look. So I'm so grateful that you didn't bother to look. So I think with that, we'll thank Thomas one more time and move on to the last talk of the morning.